Welcome to the Chapter 2 lecture on Basic Chemistry. You should use this lecture to fill out the guided notes for Chapter 2, and you should do so before you come to the Chapter 2 lecture day. So let's get started. The Chapter 2 lecture is split into two portions. The first part is going to talk to you all about atoms. We'll talk a little bit about matter and energy, and then we'll spend most of our time on how atoms are put together, with an emphasis on electrons. The second part of the chapter is going to focus on molecules, in other words, how atoms get together and form larger units and make bonds. So let's begin at the very beginning. Everything in the universe is made of this stuff that we call matter. Matter is stuff. Matter is anything that has mass that can be measured and takes up space. So everything solid, liquid, gas, and even the stuff we call plasma is made of matter. Along with matter, we have energy. And energy is the sort of force that makes matter do things. So energy can make matter move, it can make matter react, it can make matter stop. It makes matter do work. Now there are several different types of energy that exist. There is kinetic energy, the energy of motion, potential energy, there is solar energy, there's atomic energy, and so on. Many different forms of energy, and it can change from one form to another. We're going to address energy in more detail in a later chapter. There are many different types of matter that are known to exist, and each of these is referred to as an element. Elements are represented on the periodic table by those squares. Each one has its own square and its own symbol, which we'll get to. Now there are 92 naturally occurring elements that are known, and 20 plus that have been artificially created in the lab. And I say 20 plus because every year they discover new ones and add them to the periodic table. This is the periodic table of elements. Each square on the periodic table represents a different kind of matter. And you'll notice that each kind of matter is represented with a symbol, or set of letters. Now these elements are arranged by size. So here in the top left corner we have hydrogen, and it's up there by itself because it is the smallest known element. The next largest is way over here on the right, that is helium. And you'll notice that as we go from left to right on the periodic table, the sizes or the numbers above these symbols increase. Also, as we go from top to bottom, the numbers increase as well. And that's because these elements are arranged from smallest here at the top to largest at the bottom. Now, as I said before, there are 92 naturally occurring elements that are known. We are going to focus on the smallest 20. So we are going to focus on these guys. Now, why are we focusing on those? Well, these are the ones that are commonly found inside living things. Things like carbon and calcium, nitrogen and oxygen. The larger ones like xenon and radium, you don't find those so much in living things unless there's a problem. Each different type of element is represented by an atomic symbol, and that consists of either one or two letters. These are the atomic symbols that I would like you to know for this class. They're taken from elements 1 through 20, and of those, these are the most important. So you do want to memorize these before test time if you don't have them memorized already. There are rules for properly reporting the atomic symbols. Atomic symbols either consist of one or two letters, and if it's more than one letter, the first letter is capitalized and the second letter is lowercase. For instance, here we have the atomic symbol for carbon, a capital letter C, and you can see that it appears right in the middle of its box on the periodic table. So although there are many different elements that exist in nature, there are only a very few that make up living things in any large amount, and those are listed here. Living things are mainly made of carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. There are other elements that are found inside living things, such as iron and zinc, and these tend to be found in very, very small amounts, so we call them the trace elements. There is a memory trick for learning which of these elements are the most common, and it is spelled out here at the bottom. It spells out the word schnapps. So if you're trying to remember what living things are made of, remember we're mainly made of schnapps. Now this slide is sort of messed up. It looks like it got chewed up in the uploading process. But this is your first year turn, and you can find this year turn on the guided note sheet as well. What I would like you to do at this point is to pause and quiz yourself a little bit. Practice matching these symbols with their actual names. So do that, fill out your year turn, and bring that to class so you can double check it and we can talk about it. The different elements represent tiny particles known as atoms. So for instance, if you took a big lump of carbon out of the earth, that carbon would behave a certain way. It would have certain predictable characteristics. It would act like carbon. You could break that carbon down, and what you would find is that that lump of carbon is actually made of tiny little particles called carbon atoms. And those atoms, even at that tiny level, would still behave like carbon. However, if you took this atom and you started breaking it apart and chopping it up and knocking things out of their orbitals, you would find that it no longer acts like carbon. It would act like a different kind of element. So we say that an atom is the smallest level of matter, the smallest unit of matter. Really, it's the smallest unit of matter that acts predictably. Once you break it apart, it starts to play by different rules. Now, atoms have a particular structure, which we'll talk about, and different atoms of different elements have different structures. That's what makes them different from one another. Now, if you took an atom and looked inside it, you'd find that it's made of even tinier particles known as subatomic particles. These things we call protons, neutrons, and electrons. Over here on the right, we have the classic model of an atom. This is called the Bohr model of an atom, and it's actually a little bit outdated. It makes these little particles look like they're on a roller coaster ride, like they're on these little tracks and they just go around and around forever. And that's not entirely accurate. But this model is a good jumping off place for us in terms of understanding atomic structure. The first thing I would like you to do is to see what you remember from chemistry. Where would you find the protons, neutrons, and electrons? Now, I'm sure you've had some chemistry before, so I'm confident that you knew that the ones on the inside here are the protons and neutrons, and these guys flying around the outside of the atom are the things called electrons. Now, the protons and neutrons are in the center of the atom in this little area that we call the nucleus. The electrons are flying around the outside of the nucleus. Now, where are they exactly? Well, that gets a little complicated. The electrons are actually located somewhere within this three-dimensional, very complex sort of cloud that exists around the nucleus. And in general, we refer to that three-dimensional cloud as an orbital or a set of orbitals. Next, let's discuss the relative mass of these subatomic particles. Now, subatomic particles are so tiny that we can't really even measure them in grams very well, so they have their own mass unit. It's known as an atomic mass unit, or an AMU. Now, the mass of one proton is approximately 1 AMU, and so is the mass of a neutron. Down here on the diagram, you can see that these two things are approximately the same size. Now, with electrons, of course, everything gets a little trickier. Electrons are so tiny that technically it's fine to say that they have 0 AMUs. Now, that's a little tricky, right? There isn't anything in nature that is 0 AMUs in size. That technically can't exist. So in reality, if you were to look up the size of an electron, it would come out to something like 0.005 AMUs. But the mass is so tiny that we consider it negligible, so it often gets rounded to 0 AMUs. Next, let's discuss the charges that can be found on these subatomic particles. Protons have a positive charge. Oftentimes they are represented with a lowercase p with a plus sign as a superscript next to it. Now, when you hear the word neutron, you might think negative charge, but really you should think neutron is neutral because neutrons don't have a charge. Electrons are actually the particle that have the negative charge, and so they are often represented with a lowercase e and with a little superscript negative symbol. Now, protons and electrons have opposite charges, and that's actually a pretty important thing. The reason that's important is because of what we learned in basic chemistry, or maybe from what you learned from Paula Abdul back in the 90s, that opposites attract. Protons have a positive charge, and they are in the nucleus. Electrons have negative charges, and they are out here in their orbitals. And those negative and positive charges are attracted to one another. When atoms have the same number of protons and electrons, we say it is electrically stable. And it's actually this attraction that helps hold the atom together as a whole. All right, so here's a little practice for you on this opposites attract thing. If we put these two positive particles together, what are they going to do? Well, they are going to repel one another. Like charges repel, they push each other away. And so these negatively charged particles, like electrons, if we put two of those guys together, they're going to push each other away, like poles on a magnet. However, if we put oppositely charged particles next to each other, they are going to attract one another. Opposites attract, likes repel. Here's another your turn. You will find this your turn in the body of your guided notes for this chapter. So at this point, just take a few minutes and see what you can remember about these three types of subatomic particles. See if you can remember their location, their size, and their charge. See if you can fill this chart in from memory. If you have to look it up, that's fine. Either way, fill in the chart and bring it with you to class. Next, we're going to discuss what makes the different atoms of different elements different from one another. Well, of course, different atoms have different numbers and arrangements of subatomic particles. But which one's really important in defining an element? Well, it turns out that it's the protons that's the most important. We define a specific type of element based on the number of protons that it has. For instance, hydrogen, the smallest type of atom, has a single proton and a single electron. It doesn't even have a neutron. It's really tiny. Helium, the next largest atom, is really different. It has 2 protons, 2 neutrons, and 2 electrons. And it's really the 2 protons that make it behave like helium. If we took hydrogen and we jammed another proton into its nucleus, it wouldn't behave like hydrogen anymore. It would behave like helium. Incidentally, this is what happens in fusion reactions in the center of the Sun. The number of protons that a particular element has is represented by the atomic number listed next to the atomic symbol. You'll either find the atomic number listed above the symbol, as we have here, or sometimes it's listed as a subscript to the left of the atomic symbol, as we see here. Now, what this number tells you about hydrogen is that it has one proton. For many of the atoms, and especially the small ones we're going to work with, you can assume that the number of protons, neutrons, and electrons are the same unless there's some kind of symbol present that tells you otherwise. But that's not the case with hydrogen. Hydrogen's one of those exceptions. Hydrogen has one proton, no neutron, and one electron. So that atomic number really just refers to the protons. Again, it looks like the uploading process sort of ate my slide. These guys are kind of scattered around. But this is another your turn activity, and you will find it on your guided notes. What I'd like you to do for this your turn is just to practice with the atomic numbers. I would like you to look up the atomic numbers or try to remember the atomic numbers for all of these elements, and then find some space so that you can write these in order from smallest to largest in your notes. You don't have to memorize the atomic numbers for these different elements for the test, but it is good practice. And the better you are remembering these, the easier some of this chemistry stuff's going to be for you. So take a moment, perform this your turn, bring it with you to class. Next, we need to discuss the atomic mass for an element, or the approximate size, the approximate mass of one atom of that element. There are a couple of different ways to calculate the mass of an atom. The first way is a rough estimate. It's calculating something known as the mass number, which we'll get to in a bit. Assuming that the mass of one proton or one neutron is 1 AMU, you can estimate the mass of an atom by simply adding up the number of protons and neutrons that it has. For instance, hydrogen has an atomic number of 1 because it has one proton. So its atomic mass is going to be approximately 1. Now, when you look at the atomic mass on the periodic table, and it is listed just below the symbol typically, you'll notice that it's got all these decimal places after it. Why isn't it listed as just 1? Why is it 1.0079? Well, that's because there is a second way to calculate the atomic mass. If you find hydrogen in nature, you're not going to find just one form of that hydrogen. There's actually several different forms that exist very commonly, and they can have slightly different sizes. So what scientists have done is taken the average of the different types of hydrogen that exist, they average them together, and that's why they get this number with these decimal places. And they've done that for all the different types of elements that are known. Now, you don't need to memorize the atomic mass. It will be provided to you if you need it, but you do need to know it's found beneath the symbol here so that you can look it up. There are rules that exist that help us determine the number of subatomic particles that a particular type of element has. Now, the number of protons is going to be determined by the atomic number, and that number will remain constant. It will not change. Remember that if you take an atom of hydrogen and you jam a proton into its nucleus, it's not going to behave like hydrogen anymore. Instead, it's going to behave like helium. So the number of protons will remain the same. In general, the number of electrons an atom has will be the same as the number of protons, as long as there isn't a plus or minus symbol attached to it. A charge like that is going to indicate that something's going on with the electrons, and we can talk about that more later. Now, different forms of each element exist in nature. In other words, if you found a big lump of carbon in the ground, you would find different types of carbon atoms in that lump. And those atoms can differ in their numbers of subatomic particles. The periodic table represents the most common forms of each element that we find in nature. The number of neutrons that an atom has can differ from the number of protons. So to determine how many neutrons an atom has, we have to do a little math. Here's the math we have to do. To determine the number of neutrons, we need to take the atomic mass and subtract from it the atomic number and round. So for instance, if we're looking at aluminum and we take the atomic mass and subtract from it the atomic number, we end up with this number, 13.98. Now because it has a decimal greater than 0.5, we can round up to 14. And that tells us that aluminum, in its most common form, has 13 protons and 14 neutrons. If the number had come out with a decimal that was 0.4 or lower, we would round down. Again, different forms of atoms exist in nature. If an atom differs from the periodic table in the number of neutrons that it has, we call that type of particle an isotope. And we'll talk more about those in just a second. If it differs in the number of electrons, it will have a charge on it, a positive or negative symbol, and we call that kind of a particle an ion. And we'll come back to ions near the end of the chapter. Different isotopes of an element have different numbers of neutrons. Here we have some isotopes of hydrogen. Here's the most common form of hydrogen with its one little proton, its one electron, and no neutrons. Here's an isotope where hydrogen has a single neutron, and here's one where it actually has two. So these different forms of hydrogen can be found in nature, and we call them isotopes of one another. Another number that's used to represent isotopes is called the mass number. Now the mass number is a rough calculation. It represents the number of protons plus neutrons in the nucleus. So it's the number of things that are found in the nucleus. The mass number is represented as a superscript to the left of the atomic symbol. So for instance, this isotope of carbon is called carbon-14. Now, what's the most common form of carbon? Well, carbon's atomic number is 6. So in carbon, the number of protons and neutrons are the same. So the most common form of carbon is carbon-12. Oh, if I can draw a 2. There we go, carbon-12. Another way to represent isotopes is to use something called the mass number. The mass number is the number of protons plus neutrons in the nucleus, so the number of things found in the nucleus. For instance, carbon has 6 protons and 6 neutrons, so its mass number would be carbon-12. That's the mass number for the most common form of carbon. Now here we have an isotope of carbon, carbon-14. What does that 14 indicate? Well, because the number of protons will never change, the presence of 2 extra things in the nucleus must be neutrons. So the presence of that 14 tells us that there are 2 extra neutrons in that nucleus. Because isotopes have different numbers of protons and neutrons, they tend to have unstable nuclei. And so those nuclei, like this one shown here, can fall apart slowly over time and release particles. When they release those particles, they release energy. And that energy is known as radiation. So isotopes are radioactive. The small ones, like carbon, only release a little bit of radiation, so we're well adapted to that. That's not dangerous. But some of the bigger isotopes, things like uranium and plutonium, those have really big nuclei, so they can release a lot of radiation, and they can be really dangerous. The rate at which an atom releases radiation is known as the half-life for that atom. Now, even though radioisotopes can be very dangerous, they can also be really, really useful in the lab. Because radioisotopes release energy, and because we can actually detect that energy, we can use radioisotopes to track things. So for instance, here an isotope has been released into this person's body, and it's been released in such a way that it will attach only to cancer cells. Then the body can be scanned for radiation, and you can see that there's radiation showing up here in the throat. So that's where the cancerous tumor is. It allows doctors to see where the tumor tissue is. Isotopes can also be used to determine the age of fossils. We can track individual molecules through a metabolic process. For instance, you can attach isotopes to glucose and see where the glucose travels inside the body. And as I said before, for diagnosing different medical disorders. So we use radiation quite a bit in science, and it's very useful. It just has to be used carefully in order to be used safely. Next, we need to discuss electrons. Now, electrons are the smallest particles. So why do we care about electrons? Well, it turns out that when two atoms get together and they want to make a bond to form a molecule, it's actually the electrons that are going to form that bond. So we need to understand a little bit more about electrons and how they behave. The arrangement of electrons around the outside of the nucleus can get a little complicated. Electrons actually exist in these three-dimensional clouds around the outside of the nucleus that we call orbitals, and they can get quite complex. Another way to define orbitals are areas where electrons are likely to be found at any given point in time. Orbitals can have these different shapes. They can be spherical or have these weird kind of balloon animal shapes. And as you begin to combine atoms together and make molecules, the shapes of these orbitals can change. So they can get quite complex. Now for our purposes, I just want you to know that these orbitals exist, that they are spaces where electrons are likely to be found. We're going to focus more on the energy levels at which electrons can exist, something called shells. Another aspect of the arrangement of electrons within an atom, and the aspect that we are going to focus on, are these things called electron shells. Now, shells don't have so much to do with the actual physical location of an electron, so much as the energy that it has. So I want you to think of an electron shell as being kind of like an energy layer around the outside of the nucleus. Here, for instance, you can see one shell, and it has a certain distance from the nucleus. Ooh, that's terrible. And here's, oh, it's even worse, a second shell, and it's a little further out from the nucleus. So these are energy layers. Now, what kind of energy does this represent? It represents potential energy. And electrons that are in these different layers can have different amounts of energy. They will also be a different distance from the nucleus. Now, as I said, these different electron shells have different amounts of energy, and here we're talking about potential energy. Shells that are closest to the nucleus actually have the least amount of potential energy. In other words, they have the least potential to leave or to jump up to another energy level. And that's because this big old nucleus with its protons in here is holding very tightly to those electrons. It's attracting them most strongly in the first shell. Electrons in the second shell have a little bit more energy, in the third shell have even more energy, and so on. The further away from the nucleus, the more potential energy an electron has. The more potential it has to jump up to another level or to leave the atom entirely. Now, electron shells are arranged kind of like seats in something like a stadium or a concert arena, something like that. What do I mean by that? Well, if you've ever been to a sporting event or a concert, you know that the really good seats are right up here next to the stage or right up here next to the field. And those are really expensive because they have the fewest number of seats. In the same way, the shells that are nearest the nucleus can hold the fewest electrons. Those are the really good seats. If you go back a few rows, well, those rows are actually bigger, so they can hold more electrons. And if you go way back here into the nosebleed section, well, those are the cheapest seats because they can hold the most electrons. So these different energy levels can only hold certain numbers of electrons, and that number tends to increase as you go from the nucleus out. Here's another really fun example or illustration of this concept. Here we have a balcony. This balcony is going to represent our first shell that's nearest to the nucleus. This shell contains one old person. It has room for 2 old people, however, and so now that a second old person has joined the first, that shell is now full. There's no vacancy there. So an atom that has more than 2 electrons has to have a second energy level, a second shell, to hold that third electron. So each electron shell can only hold so many electrons, and in general, the closer to the nucleus it is, the fewer electrons it can hold. Here are the rules for the first 3 shells. Shell number 1, which is closest to the nucleus, can hold 2 electrons, and that's it. So if an atom has more than 2, the rest of those electrons have to go to the next shell. Shell number 2 can hold an additional 8. So an atom with a maximum of 10 could use those 2 shells by themselves. And then the third shell can hold a maximum of 8 electrons. Now, if you are very chemistry savvy, you'll know that that third shell can actually hold 16. But after we have a maximum of 8 in that third shell, the electrons tend to start jumping up to the fourth shell and doing some weird things. So for our purposes, we're going to think of the numbers as being 2, 8, and 8. There's only one example of an atom that will get larger than this, that's calcium, that we will use in this class. So we're going to stick with the easy numbers here, 2, 8, and 8. Here's a couple of examples of different kinds of atoms with different sizes that use different numbers of electron shells. Here we have good old hydrogen again, super tiny hydrogen. It has one little electron, so it can put it in its first shell, and it's perfectly fine like that. Now you'll notice that hydrogen actually has room on its shell for one more electron if it can find it somewhere, because that shell can hold 2. Carbon, on the other hand, has an atomic number of 6. So in its natural state, it's going to have 6 electrons. It's going to put 2 on the first shell, and now that shell is full. It has 4 additional electrons, so it's going to put them on the second shell. Now let's think about this. Is that shell totally full? Well, no, because the second shell can actually hold 8. So potentially, carbon could put 4 more electrons in that shell. And that's going to be how it begins to make things like covalent bonds, which we'll get to in a little bit. These diagrams, such as the one shown here, are known as shell models. And shell models are useful because they show the number of shells that an atom uses and the arrangement of the electrons. So this, for instance, is the shell model for carbon. Now, the shell of most interest is this one out here, and I'm terrible at tracing, but you get the idea. This is known as a valence shell, and valence shells are important because when 2 atoms get together to make a bond, to make a molecule, these are the shells and the electrons that are going to interact. So it's important to be able to identify the valence shell of an atom. In this your turn, I'd like you to use what you've learned about the arrangements of particles inside atoms to draw some shell models. So I want you to draw the shell models for oxygen, nitrogen, phosphorus, and sulfur, and bring those to class with you so we can compare them and discuss them.